Okay, so today we're talking about something, this won't take long, this might take only 10 minutes, and that's fine, because then we can practice some of the sort of Yates order things. Okay. Most designs assume equal ends. Okay. There's an assumption being made that I haven't even mentioned typically that just says the ends are equal. When we talk about breaking down a table and looking for main effects and interactions like we're doing here, that I'm working with the assumption of equal ends in each group. Okay. Except for the very simplest ones like this simple one-way analysis of variance, one way between the first thing you talk about, the thing you learned in your first stats class. Okay. Well, what if your ends aren't equal? Happens. If you look back at the formulas, and I don't expect you to do that right now, but if you did look at the formulas, they always have just the letter N in them. They're basically saying the number of subjects in each group, and that is then saying, well, that must be equal. All the things we do, we break down those Yates order things, assume everything's equal. Well, what would you do? Or as Lenin once said in a pamphlet before the Russian Revolution, what is to be done? Very few people make references to Lenin. Vladimir Lenin, not John. Maybe we can estimate the missing values. That's a possibility. So, a lot of times, and you'll see, in fact, SPSS and every other piece of statistical software out there will have a thing telling you a thing about an option. What do you do with missing? And you'll say like missing or missing values, and you can make various guesses, which is what they are. Well, they're estimates, but they're not very far from guesses. You can use the mean for the cell or the median for the cell. There's nothing wrong with that. Like they're common enough. Do you include? When you're guessing this thing, you say, I'm going to put main effects in. Do I also put the interactions in? Now, there's a lot of choices you can make there. You can let the software do it. You can make these things. You can say, do it without interactions, do it without main effects, whatever. But one thing you have to remember is you've lost degrees of freedom. Or you don't, well, I guess if you lost them, you don't get them. So if I put in 2 extra numbers, that doesn't mean I get, when I do my analysis, I go up a degree of freedom. It stays where it is, because I fixed other values. Okay, does that make sense? Okay, you gotta keep that in mind. And in fact, if the software is doing it, if it's making these guesses, it'll take care of that for you. So that's cool. Like it'll say, give you an output and it'll give you the correct degrees of freedom. So that's okay. There's an easier way to handle this, and that's, just collect a couple more data points. That's what I would do. Now, there are other ways to deal with this. Most of our analyses use something called type 1 sums of squares, you're saying. So that means there's other types. Oh, yeah. The type 1 sums of squares are the ones that I've shown you with all those summation signs. They're the ones you've learned about since you started learning about sums of squares in Stat 2126. It always works this way, doesn't it? You're told something for years and years, and then you're told, yeah, but it's way more complicated than that. In grade 9 science, you're told that atoms you got protons and neutrons, and then there's electrons rotating around them like planets around the sun. And then you get to, I remember it was grade 13 chemistry, which you guys don't have anymore, but whatever, probably grade 12, and you go, actually they're quantum probability clouds. You go, what? And the world's more complicated than you thought. There's more kinds of sums of squares than type 1s. By the way, type 1s assume equal ends. Remember that from looking, again, you look back at the formulas, they show that the ends are equal. They don't work when you have unequal ends. And some of you might be wondering, we have one person in the room, Sam, you're doing data analysis right now. Did you have equal ends or not? No. But did you notice when it came out, it didn't give you any horrible warnings or anything, right? So you're okay. Perhaps it used type 2 sums of squares. Type 2 sums of squares are great because you're missing it. They're okay if there's a missing value. I'm not even going to tell you how these are calculated. You don't want to know. It's like knowing how the sausage is made. You just don't want to know this. If there's an interaction, they don't work. It's not like no numbers come out if there's an interaction. Like, well, I can't do that, math says. No. What happens is it just doesn't work properly, and it underestimates the main effects. And it can't deal with interactions. It's like, oh. Well, there's got to be something better. And Sam, if you look at your output, you will see that it says type 3 sums of squares at the top. In fact, anybody else here who's used SPSS to do anything ANOVA assignments realize it says type 3 sums of squares. Type 2s are fine if you don't know if there's an interaction or not. Sorry, if you know there's no interaction, there just can't be, then you're fine. They, by the way, do have, you might think, why would such a thing exist? It actually has a use, and we'll talk about it when we talk about multiple regression. But type 3s are great because if you have the interaction or not, they work. So, in fact, the default output that you get from any statistical software is type 3 sums of squares. They are calculated using matrix algebra, which is, again, something you don't want to know about. You may be unlucky enough at some point in graduate school, if you're in graduate school, to run into how to calculate these by hand. Oh, what a hellish nightmare that was. Hopefully they don't do that, because it's ridiculous. Conceptually, it's okay. I remember my PhD one year, we're reading statistics journal articles. Boy, that was fun. Good times. Really living on the edge. So we've learned type 1 analysis because conceptually, it's ways to get your head around. But the software will always use type 3. The nice thing is, if you have equal ends, the type 1s are the same as the type 3s. They come out computationally equal. Okay, that's good. So I haven't been wasting your time. Well, maybe I have, but at least not with this. So if the ends are equal, type 1 is equal to type 2 is equal to type 3s. That's great. So it just defaults to giving you type 3s. So you don't have to really worry a lot about this. I still prefer, like my students, when they ever have unequal ends, I tell them, just go collect more data, please. Just go collect more data. It makes doing post-hocs easier. There's a lot of things that makes it a little bit easier. Just go collect more data. You need to run one more person. Just find some guy, pull him in against his will, force him to do a questionnaire. Okay, don't do that. That's unethical. You can't force me. I'm kidding. I'm kidding, Research Ethics Board. I'm kidding. Talking directly to the microphone. But you can usually find one more person that'll do it, or 2 more people. So it's just easier. It's cleaner. There's a type 4. Yeah. Type 4s are great. They're good for what's called empty cells. What if you collect data and you've got a whole, look, we have right up here on the board a 2x2, A1, A2, B1, B2. So we have 6, 4, right? So we got 6 in A1, B1, we got 6 in A1, B2, we got 4 in A2, B1, and we got nothing here. We didn't collect any data because we're kind of slow. Why would you do that? Why would you miss? Why would you think, I'm just not, well, screw that, that one can't be important. And that's when someone says, when you're doing your practice talk, and what happens a lot of times is you actually miss these things because you're so close to your own data. You and your supervisor, if you're doing your thesis, you're so close to your own experiment that you don't even realize that, why isn't this here? Because you thought it was a 3-group design. It's like, well, why isn't there an A2, B2? Well, it's right here. Right, that's enough.
And your shoes untied.
I don't care about my shoes.
Okay.
I'm living on the edge of the shoe. Make my whole t-shirt fall apart? That'd be weird. Some of these things I edit so much out in my head. So type 4 sums of squares could actually do this. Maybe I will tell them. I should have thanked you. Yeah, so well, let's go type 4 sums of squares. It'll tell us if there's an interaction. Now, I think the somewhat sophisticated among you will realize there's really no unique solution to this. It'll come up with an answer. It's more matrix algebra, so I'm not going to tell you how to do it. But it literally comes up with, it changes, the values of the sums of square change depending upon the order you actually do the calculations in. Let's type 4 sums of squares. Oh, that's really useful. So there's really no unique solution. And here, let me just show you what I mean. What goes here? That's what type 4 sums of squares are trying to figure out. What should go here? Just give me a number. What do you think?
7.
How about 7? Why not? Sure. How about 4? Makes it look, 4 here, 2 here, 2 here. What about 0? So it goes down by 2, down by 2, down by 2. Ooh, that seems nice and symmetrical. What about a trillion? What about pi? It just, you can't know. So doing an analysis like this, using type 4 sums of squares, is an academic exercise. It's actually not a useful data analysis tool. The best thing to do in this situation, well, there's 2 things. The first thing to do is actually just now analyze this as a 3-group, one-way analysis of variance and give up on talking about interactions. That's the first thing to do. Probably the best thing to do is go collect the data. Why not go get some A2, B2 people? Right? Don't do a type 4 analysis. The best way, as my old stats prof Ian Spence used to say in Toronto, the best way to analyze data with empty cells is not to collect it. Just don't design experiments like this. He also used to say the best way to analyze the unbalanced designs, in other words, designs with unequal ends, is don't do experiments like that. Do them with equal ends. It just makes everybody's life easier. It's not a huge deal, but it makes things like post hocs and stuff a lot easier to do. So it's an odd thing to think about. It's just one of these, this is sort of a tack-on thing I throw in at the end, and it's simply because this is something that every year somebody misses something like this. Not this badly. But every couple of years this happens. Every couple of years this happens. I also once, a friend of mine, this is not in the field that I'm in, but a friend of mine at another school was telling me how he got an article to review, and it had a correlation in it, and you can just look up correlations. Significant is a t-test, doesn't matter, it's pretty easy. And it turned out it wasn't significant. So in the method section, they said, so what we did, because it wasn't significant, is we just simulated we doubled the number of scores, just used the same numbers again twice, and now it's significant. That's just making up data. You can't do that. Happily, it was caught and never got published that way. This is one of these things, just don't do this. Questions about that? I think you probably all understand. All right.